So let's look at the Michelson-Morley interferometer, or just an interferometer. It doesn't have to be a Michelson-Morley interferometer. This is a standard piece of equipment. The Michelson-Morley experiment was looking for the ether, but we can use an interferometer like they used to look for all kinds of things. And let's say that we want to, let's say, measure the index of refraction of a gas. Right? Index of refraction, remember, has to do with how fast the gas moves through, how fast light moves through the gas. So assume that the Michelson-Morley experiment, the interferometer is in air or vacuum, which is very much like air in terms of speed of light. But along one of the legs, we can put a container of a gas that we want to measure the index of refraction of. So what that does is it slows down the light traveling. I put it in path 2, so it slows down the light traveling in path 2. So I can have no gas in it, look at the diffraction pattern, add gas, and see if the diffraction pattern shifts. If the amount that the diffraction pattern shifts by, the amount that it shifts from when there was no gas to when there is gas, tells us how much path 2 has slowed down compared to path 1. If it's slowed down by 1 wavelength, then the entire diffraction pattern will shift over by 1 dot. Make sure you understand that. If path 2 is slowed down by half a wavelength, the entire diffraction pattern will shift over by half a dot. Right? So path 2 doesn't have to be slowed down by much. Half a wavelength for light is a very small amount of distance, right? If the light is 700 nanometers, then that's 350 nanometers. So this is sensitive to slowing down the path 2 by a very small amount. And I say slow down, you say, oh, doesn't that mean speed or time? And I'm giving a distance. Well, it's traveling at about 3 times 10 to the 8th meters per second. So if we know it's traveling at 3 times 10 to the 8th meters per second, and it's slowed down by 1 wavelength, then we can figure out how much time it was slowed down by. So those are all connected. They're all connected variables. But again, we're looking at slowing down one leg, delaying is probably a good one, delaying one leg by a time which is equivalent to a number of wavelengths. And if we delay one leg by a whole wavelength, we've shifted the whole pattern over by 1 dot. Or if we shift it by half a dot, then we've slowed down one path by half wavelength. Okay, so let's just go to the Michelson-Morley experiment rather than doing this. So what Michelson and Morley, or what Michelson initially in 1881 did by himself and then did with the help later, was recognizing that light traveling through this ether, right? The ether, remember, is at the time known or thought to be the preferred frame of reference for the light. So the ether is hanging out on the Earth's surface, right? But it's probably but why would the ether be stationary relative to the Earth's surface? That actually doesn't make any sense. It doesn't physically make any sense because the only place that light doesn't just exist on Earth. Light exists everywhere in the universe. So wouldn't it make more sense to have maybe the ether is in the frame of reference of the sun, or the ether is in the frame of reference of the center of the universe, or the center of the galaxy? I don't know, but there's no need for it to be. We're not egocentric, right? We're not. The ether doesn't belong only on Earth. And you might say, well, but doesn't it, like we have an atmosphere on Earth that's relative to Earth, doesn't it slow down? Well, I mean, light is different than those things, right? But you say, maybe there's ether drag. They actually call that ether drag. It's slowed down by the Earth. But in order to do this experiment, we do have to assume that there is an ether wind, meaning the ether moves relative to the stationary lab frame. Okay, so with that assumption, let's say that the ether moves, like that gravitational wave, the ether moves in this direction. Oh wait, the ether is not a wave, sorry. The ether moves in what I guess in this picture would be the plus x direction. So let's just assume that the ether moves in this direction. And the ether moves with speed v. And what that means is that, and it doesn't necessarily move in that direction, right? And the way Michelson and Morley accounted for that is by doing this experiment at one orientation and then shifting the whole experiment 90 degrees. So we'll talk about that later. Okay, so let's just assume that the ether is moving in this direction, along the path 1, right? So that means that if the speed of light, right, the speed of light is c, the speed of light is c relative to the ether. C is about, we already certainly knew in 1887 the speed of light was about 3 times 10 to the 8th meters per second. So just keep that in mind. That's important for some approximations later. So if the ether is moving at v and the speed of light is c relative to the ether, then relative to the lab frame, relative to the experiment frame, the light must be moving in that direction at v plus c, right? So the light must be moving in that direction at v plus c. And you might say, well, why can't we just measure that? And why do we have to do the Michelson-Morley experiment? Well, remember, speed of light 3 times 10 to the 8th meters per second. If the ether is moving at 30 meters per second, we're never going to be able to measure the difference between 3 times 10 to the 8th meters per second and 3 times 10 to the 8th meters per second plus 30. That's just too small a percent difference to be able to measure, certainly in 1887. That also means that any light, right, so if you follow path 1 has light going to the right, I'm drawing over path 1 right now, which would travel at v plus c, but then it has light bouncing back, which is traveling at what speed? Light going in this direction must go at v minus c, okay? Now note that when we figure out what's going to happen to this diffraction, this interference pattern, also called the diffraction pattern sometimes, but anyway, the interference pattern, that all that matters is what happens in this part of the path and this part of the path, because the light in this part of the path is traveling together, and the light in this part of the path is traveling together. So whatever happens to one beam happens to the other beam. But when they are treated differently is when they're along those two parts of the path. That's when the light would take a different amount of time. The other two parts of the path, the light must take the same amount of time because it's traveling together. Okay, so we can figure out how long. So what we want to do is figure out how long it takes the light to travel along path 1, both forwards and backwards from the beam splitter to the mirror. And then we want to do the same thing for path 2, from the beam splitter to the mirror, the two yellow paths. So let's just take path 1. Path 1. Let's assume that the length of path 1 is L. L in one direction. So the light is traveling a total of 2L. So how long does it take for the light to traverse path 1? You can say T1 is equal to, how long does it take? Well, distance equals rate times time. Light travels at constant velocity. Constant velocity in one direction. Now with the ether, it might be traveling at different velocity, left from right. But anyway, it's distance over v plus c. That's the amount of time it takes to go from the beam splitter to the mirror, plus L over v minus c. That's the time it takes to go from the mirror to the beam splitter. Hopefully, you just figured out that I did something wrong. And what I did wrong is I said v plus c and v minus c. It should be c plus v and c minus v. That's just algebra. Think about it. Actually, that's not entirely true either, because if we were talking about vectors, what I said before would have been correct because it would have been positive in one direction, negative in the other direction. But actually here we're only talking about scalars because I want to know the total time it takes. The vector, right? The displacement in the end is 0, so the average velocity is 0. But I want to know the total time that it takes. So it's just scalar quantities. So it would be really the absolute value. So I guess it wasn't really wrong to say v plus c and v minus c, but it would be the absolute value on the bottom here, whatever. Okay, so this is the amount of time it takes to go path 1. Now what about path 2? That's a little bit more complicated. Path 2.
And we will do that next time.